I think we're ready to go. Really nice to see so many people interested in GC. My name is Stefan Johansson. I work at Oracle as a software developer. I've been doing GC in OpenJDK and Java for the past decade or so, and this presentation will cover some of the things that we've done over this past 10 years. I have two main goals with this presentation. First, I want to give you a better understanding on how to choose the correct garbage collector for your application. But I also want to show all the benefits you can get from upgrading to a more recent release of Java compared to maybe JDK 8, which I know have been heavily used in the past and still is. So with that, I want to welcome you to this talk, Garbage Collection in Java, the progress since JDK 8. Let's start off with the agenda. So I'm going to start off talking a bit about GC in general in Java, and then look closer at the different collectors that you do have, before spending a pretty big part of the time of this presentation on the performance benefits or improvements that we see since JDK 8. I'm going to show some success stories from the real world, and then finish off with a few words about the future. So let's get into it. Garbage collection is a key feature of the Java platform, and it's a type of automatic memory management, and it has two key things that we want to support the overall performance of the Java platform, and that is fast allocation and efficient reclamation. How we handle the fast allocation is more or less the same regardless of the GC algorithm you're using. So we're having something that we call TLABs, thread local allocation buffers. Those are handed out by the GC to the allocating Java threads, and then the Java threads can do synchronization-free pointer bumping allocation, which are really fast. Once the TLABs are full, they are handed back to the GC to be handled. And this is where you have some synchronization. But overall, the allocations are done very quickly, and it's handled more or less the same regardless of the GC you're using. What's different between the different GCs is how we do the efficient reclamation. And the reason that we have many different GCs is that they serve different use cases. So as you all know, Java is a really big platform, and we need to support a wide variety of use cases. So for example, we have batch processing workloads, we have UI applications, we have small cloud services, and basically anything else that we need to support. So it's very hard to create a single GC that can support all these use cases. So let's look a bit closer when it comes to memory reclamation. There are a set of problems that you need to solve to be able to reclaim the memory, and some few strategies that you can use to do this. First, what we need to do is we need to determine the liveness. So we need to know which Java objects are still in use. And we do this by tracing the object graph. What we mean by this is that we start off with a well-known set of roots, and then we follow those root objects. It could be objects on thread stacks or static fields and classes and other things that we know must be kept alive for the application to work. And then we follow the references in those objects to other objects, and doing so for the whole Java heap or the part of the heap that we're currently collecting. And that way we know which Java objects we need to keep alive. When we know what to be kept alive, we can start reclaiming the memory. And there are a few different techniques here as well. For example, you could have free lists, keeping track of where do we have free memory, or you can do something that's the most common solution in OpenJDK. You can compact the objects that are still in use by copying them to a new location, and then free up the initial location where the objects were allocated. Something else that you need to decide when you design a GC algorithm is when do you want to do this GC work? When should we determine the liveness, and when should we do the reclamation? Do we do that stopping the world, that means stopping the Java threads, or do we do it concurrently with the Java application still running? Depending on the choice here, you get different performance characteristics for the GC, and yeah, one of the reasons for having multiple GCs. And then, of course, we need to make this very efficient to have great performance for the Java platform. There are many different techniques here, and I'm just going to mention one of the most important ones that we use in Java, and that is having generational collections. This is a technique to avoid collecting the whole heap at once. So what we do is that we divide the heap into a young generation where newly allocated objects are put, and then we have an old generation where we put objects that have been around for a few user cycles. That way, we can collect the young generation more frequently, and hopefully at a lower cost. This depends on or makes use of something called the generational hypothesis, which says that most of the time, newly created objects are only used for a short period of time. So the hope is that the young generation is fairly cheap to collect because you don't have to handle a lot of objects in those collections. Eventually, the old generation will have to be handled as well, and that can be quite costly depending on the GC algorithm that you're using. So, choosing your EC, this is very important. You need to figure out what is the main focus for your application. What do you care the most about? Do you have a lot of data that you want to process very quickly, or do you have an application where the worst case latencies are very important? We mainly talk about 3 different focus areas or aspects here, and the first being throughput. And what we mean by that is mainly the raw number of transactions that are going to complete in a set amount of time. The next being latency, and that's more about the time it takes to complete a single transaction. So for example, if you have long GC pauses, that will affect the latency. The third aspect is footprint, so mainly the overhead in terms of memory and CPU caused by the GC algorithm. So you need to figure out what's the most important of those. And from a GC developer point of view, it's very hard to optimize for all of these at once. So usually we have to do a lot of trade-offs, or some trade-offs to be able to support a specific use case or maybe optimize for 2 of those. So if we try to illustrate a trade-off like this, we can have a collector that, or an illustration that looks kind of like this. So we have a set of application threads that are running. At some point, we realize that we need to do some GC work. We do that in a GC pause, stopping the Java threads, but we use multiple GC threads to do this work as quickly as possible before letting the application threads run again. So from a throughput perspective, this is very good because when the application threads are running, we're not using any CPU resources for GC work. But from a latency point of view, you can see the GC pauses, and they will inflict some latencies on your application. If we instead want something that is a little bit more latency aware or latency efficient, we can have something that could be illustrated like this. So still some application threads running, we run into a GC pause, but that is much shorter. But instead, once the application starts to run again, we do some GC work concurrently with the Java application running. And this, of course, comes with a slight throughput cost because the application threads need to compete for CPU resources with the GC threads. But from a latency point of view, this will be better. So in OpenJDK today, or in Java, we have 5 different collectors. It's the serial collector, which has its main focus on having very low memory footprint. The parallel collector, which is throughput-oriented, so trying to provide very good throughput. G1, which has a balanced performance profile, trying to have both good throughput and controllable latencies. Then we have the newest members to the GC family, which is CGC and Shenandoah. They both aim at providing very low latencies and trying to solve basically the same problem. At Oracle, we maintain 4 of those. That is serial, parallel, G1, and CGC. And those are the collectors that I will be including in the rest of the presentation. So let's take a closer look at the different collectors. So let's start off with serial. It has very low memory overhead, as I mentioned. So mainly if you have an application where you don't expect a lot of GC maybe, but you don't want it to spend any more resources, serial could be a good choice. Serial supports generational collections. So the heap layout you see here, we divide the heap into a young generation and an old generation at startup. So it's not a very flexible heap layout. Serial does its collections stopping the world and only using a single thread. So if you have a large heap, this might not be the best from a latency perspective. On the other hand, if you have something like a small cloud container, you might only have a single CPU. And in those use cases, serial might actually be a pretty good collector to use. Moving on to parallel, as mentioned, throughput-oriented, so very good for batch processing workloads and stuff like that. It also supports generational collections. Heap layout is very similar to the one of serial. So heap is divided upon startup to a young and old generation. The big difference is that parallel is using multiple threads doing its stop the world collection. And as you can see, this is the same illustration as I had before. So truly a throughput-oriented collector, but still trying to minimize the pauses by using multiple threads. The big problem with parallel is that eventually the old generation might fill up. And since all the GC work is done stopping a world, at some point you might need to collect the whole heap at once. And then parallel might inflict some pretty bad worst-case latencies. Parallel was the default collector up until JDK 8. So if you have services or applications running on JDK 8 or earlier, it's very likely that you're using parallel unless you've specified something else. Moving over to G1, as mentioned again, it has a balance between latency and throughput, trying to avoid those worst-case latencies that parallel had. And there are two main features in G1 to avoid those worst-case latencies. The first being that G1 is region-based. So instead of dividing the heap into a young and old generation at startup, we divide it into evenly sized regions that can then either belong to the young or old generation. And they can, of course, also be free if they're not in use. And a region is not tied to a generation for the lifetime of the application, but that switches over time. The other important feature of G1 is that it supports concurrent marking of the old generation. So that means that we can determine the liveness information of the old generation while the application threads are still running. So if we look at this illustration, we see it's very similar to parallel, but we also add, we also add some additional concurrent work to the GC. Having those two makes it possible to do something called mixed collections. And mixed collections are basically collecting the young generation together with a set of old generation regions. And that way, over a set of mixed collections, we can collect the whole old generation without having to have a single very long pause. And this way, G1 can avoid the worst-case latencies that you sometimes see with parallel. We've worked quite hard to try to make G1 fairly easy to tune. The main tuning knob in G1 is the pause time goal. It has a default value of 200 milliseconds, meaning that we aim to have a 200 millisecond long pauses with G1. And historically, this has shown to be a pretty good default value, but there have been talk about trying to lower this to steer G1 towards the future where 200 milliseconds might be a too long GC pause. But mainly, if you want to try to get better latencies with G1, try tuning the pause time goal down to something like 50 or 100 milliseconds. And if you want better throughput, you can try raising this value to something larger than 200 milliseconds. We made G1 the default collector in JDK 9. So anything running on a newer JDK and not specifying your GC will likely be using G1. That brings us to the newest edition, CGC, which has its main focus on low latency, but also wants to be very scalable. And the goals here is to have sub-millisecond pause times and be able to handle terabyte heaps. And we want to be able to handle those terabyte heaps without having to sacrifice any pause time. So still have a sub-millisecond pause times, even if the pauses or even if the heaps are extremely large. CGC also has a region-based heap. From an overview, it's very similar to G1. Implementation details differ a bit, but still a very flexible heap layout similar to G1's. The big difference compared to G1 is that CGC does its collection work fully concurrent. So all the heavy GC work is done concurrently with Java application threads still running. So as you can see in this illustration, the GC pauses are extremely short, but instead we have more GC work going on alongside the application threads. And the GC pauses, they are still here, but they are mainly synchronization point to make sure that the GC and application agree on what phase we're currently in. So for example, are we in the marking phase determining liveness, or are we in the reclamation phase where we move objects and update pointers? To be able to fully support this in an efficient way, CGC makes use of something called load barriers. And this is highly efficient code, highly optimized, to allow the Java threads to determine whether the object they are about to read is okay to use right now, or if we need to update where it's located, or if we actually need to help out the GC and move the object ourselves. So in some cases, with a concurrent collector, the Java application threads might actually help out doing some GC work. This will, of course, come with a slight throughput cost in some cases, but in many cases, this won't even be noticeable from a throughput point of view. We added generational support to CGC in JDK 21. So prior to that, CGC only had a single generation. So the heap layout I'm showing here is for the generational version. Going forward, we're hoping to make the generational version of CGC the default one of CGC, not the default GC, but the default version of CGC. So hopefully already in JDK 23, but we'll see about that. Yeah, so let's summarize this. So we have the serial collector, low overhead, suitable for small containers. We have parallel, great throughput, suitable for workloads where long worst-case latencies are acceptable. G1 has good throughput, controllable latency, and is suitable for long-lived services where the heap sizes are below 16 gigabytes. G1 can still handle much larger heaps. It's just that in those cases, CGC might be a better alternative. Then we have CGC, good throughput, ultra-low latency, and suitable for long-lived services where the heap sizes are above 4 gigabytes. Same as with G1, CGC can handle smaller heaps, but usually it shines more the larger the heap gets. With that, I'm done with the general introduction to Java, and I'm being very fast. So in this next part, I want to talk about the performance improvements that we've seen since JDK 8. And before we look into charts, I want to start off with some general statements about performance in GC and in Java. So JDK 8 was released over 10 years ago. So this means 10 years of development since then. So of course, we're gonna do some significant improvements. And we can see those significant improvements across all areas. And here we can interpret areas as two different things. And if you look at areas such as GC, JIT compilation, the JDK libraries, the features in the JDK, all those have improved significantly. But also within GC, we've seen significant improvements across all areas. So for example, we have shorter pauses. We've worked very hard on making the work we do inside the GC's pauses more efficient, making sure we don't spend additional resources that we don't have to. We've also worked extremely hard on lowering the memory overhead, especially for G1, which has had big problems with this in JDK 8. And overall, we have better throughput with all the collectors. And you might remember that I said it's very hard to optimize for all these aspects at once, throughput, latency, and footprint. And the way we've been able to do this is that we've been able to come up with better trade-offs than what we did in the past. So we've cut away some old trade-offs, come up with new ways of implementing things to avoid a lot of performance hits. And of course, one of the big things compared to JDK 8 is that the Java platform now has low latency collectors, which makes Java suitable for even more use cases. So that's pretty great. Now let's move over and look at some charts. Here I'm using a benchmark called SpecJBB 2015. It's developed by the Spec organization. It's a very well-known Java benchmark. And it's especially nice to look at from a GC point of view because it creates two different scores. It has a throughput score, which mainly shows the improvements for the whole Java platform, but it also comes with a latency score, which we'll look at the next slide, which is throughput with latency constraints. So you look at the throughput, but you also check like what server level agreements do we have? How long are the application latencies? I also don't want to try to show which collector is the best one, so I'm comparing the collectors individually, so with normalized scores, and the main reason behind that is depending on the heap size you would use or the machine you would use, the different GCs would look differently good. So this is run with a 16 gigabyte heap, but we're comparing the collectors individually to see the progress since JDK 8. So with that said, let's start off with parallel. So compared to JDK 8, we see about a 30% improvement when going to JDK 17. Then the improvement from 17 to 21 isn't as big. But we should also remember that between JDK 8 and JDK 17, we had almost 7 years of time. or even more than 7 years, I think. And from JDK 17 to 21, we only had 2 years. So there was a lot of more time to improve things between JDK 8 and 17, and also there was a lot more low-hanging fruit to be improved on. If we move over and look at G1, the improvements are even more impressive. And one of the reasons for this is that for this benchmark in JDK 8, G1 was a bit worse. There were even more low-hanging fruit to improve on. But still, seeing a 45 to 50% improvement between JDK 8 and JDK 17 and 21 is pretty amazing from my point of view. If we move on to CGC, we can't compare against JDK 8 because CGC wasn't around back then. But instead, I'm comparing towards JDK 17 because that was the first long-term support release where CGC was fully supported. And then I'm comparing it against the single generational version in JDK 21 and the generational version in JDK 21. And as you can see, there seems to be a slight regression between 17 and 21, but I actually think that's in the noise because we mainly didn't do any changes to single generational CGC in this time frame. We focused all our efforts on bringing generational CGC into JDK 21. And as you can see, that paid off from a throughput perspective. Gained around 10% of improvement. And it's also nice to see that these improvements really show up in the throughput score as well. If we move over to the latency score instead and start with parallel again, we can see that the improvements are even bigger, and we also see some improvements between JDK 17 and 21, which is nice. And yeah, the progress here is pretty nice to see. When it comes to parallel, we haven't spent a lot of time on that collector since JDK 8. We've done some few changes. For example, one of the things that we did was to change out the underlying threading system for parallel to use the same one as G1 and other collectors, and that really showed some benefit. So streamlining your development and your implementations can really help out in many use cases. If we move over to G1, we see even greater improvements in this score. Again, depends a bit on the fact that G1 didn't perform as well in JDK 8, but seeing a doubling in the score is certainly really impressive. And we're really happy with all the work that we've done to be able to achieve this. Then some 5 to 10% improvements between JDK 17 and 21 as well is pretty nice to see. And we're continuously trying to improve on this. So yeah, keep upgrading, usually what I say. When it comes to CGC, we do see like a 5% improvement, but improving the latency score for CGC is extremely hard because CGC has so short pauses, so the GC is not really the reason for the long application latencies. And to show this even better, I have some slides showing the pause times. So we're looking at the P99 pause times here for Spec JBB 2015. I'm using a slightly different mode of Spec JBB for it to make sense to look at pause times. So here I'm running with a fixed load and looking at how long are the pause times for this load. So for parallel, again, the collectors are in this slide compared individually. We have been able to cut away about 40% of the pause time, which is pretty great. Not too much happened between 17 and 21. For G1, cut the pause in half, basically. And when it comes to CGC and generational CGC, we did manage to cut away some part of the pause time in single generational CGC as well. Not entirely sure what that is, but with generational CGC, we were able to cut down the worst case latencies a bit because we came up with a different way to handle termination to lower the worst case latencies there. So that's pretty nice. And to really show why these improvements in CGC pauses don't show up in the latency score, I want to show you the raw numbers as well. So make note, this is a logarithmic scale, because otherwise the CGC pauses wouldn't even show up. So for parallel and G1, basically we cut down the pause times from somewhere around 100 milliseconds down to mid-60s, which is still a great improvement. It doesn't look like this on this slide because of the logarithmic scale. But when it comes to CGC, we have pauses in the realm of microseconds. So from JDK 17 and 150 microseconds down to 120 with generational CGC. That is super nice to see, but that improvement won't affect your application latencies that much since the pauses are so short. The last thing I want to show from SpecGBB is the footprint. And here we're looking at the peak native memory overhead. And for parallel, not a lot have changed in this area. Parallel was pretty efficient in JDK 8, and we haven't spent a lot of time trying to improve parallel. Now we actually have ideas on how to improve parallel in this area, but since it wasn't a problem in the past, we haven't worked on that yet. A collector that had problems in this area was G1, and one of the big problems that we heard about for G1 in the JDK 8 timeframe was the high native memory usage caused when using G1. And the main reason behind this is an internal data structure in the GC called the remember sets. The remember sets are a data structure that we need to be able to do those region-based collections that I mentioned earlier. So we need to keep remember sets to know which pointers to updates in different regions. And in JDK 8, those remember sets were kept around all the time, even though we only really need them when we collect a region. So we don't need the remember set for old generation regions unless we're about to do mixed collections. So we came up with a solution to rebuild the remember sets for the old generation regions while we did the concurrent marking of the old generation. And that way we are able to cut down the memory usage almost in half. So from 1.9 gigabytes for a 16 gig heap down to 1 gigabyte is pretty incredible. So a lot of work went into making those data structure efficient, and it really paid off. Between 17 and 21, we then came up with another way to cut away an old deficiency, and that was to get rid of one of the marking bitmaps that were present in G1. And a marking bitmap is a data structure keeping track of the liveness information for the old generation. And G1 had two, basically be able to do some verification and keep track of things. And we came up with a better solution, only requiring to keep one of the marking bitmaps around. So this way we were able to cut away a few hundred megabytes more, which is pretty nice to see. And this ID might be in some sense transferable to Parallel as well, because Parallel also has multiple marking bitmaps, and we do think that there are solutions to only keep one of them. So maybe we can improve on Parallel in this area as well. Moving over to CGC, we actually do see the first regression, but I'm not sure we can call it a regression because generational CGC is a completely new mode of CGC, and adding generation comes with a cost when it comes to memory usage, because you need to keep track, similar to the remember sets, you need to keep track of pointers between different regions in CGC, and you need to have forwarding information that you didn't need when you just had a single generation. So this was all expected. The overhead is somewhere around 20% in this compared to single generational CGC in this case. From my point of view, it's totally worth it because generational CGC makes it suitable for so many more use cases and improving the performance in so many other ways. So we're quite happy with this, but we plan to try to improve on it. That was that for the benchmarking slides. Now I'm going to head over into a section with some success stories from the real world. I'm going to start off with Netflix, which some of you might know is a very large Java user. They have a large stack of Java application. They've worked hard on being able to upgrade to newer releases, making sure that their internal infrastructure is up for doing JDK upgrades. And in 2022, somewhere around that time frame, they started upgrading to JDK 17, JDK 17. And they saw significant performance improvements by doing this. And most of their applications using JDK 17 are using G1. And here is a chart provided by Netflix some years ago from the upgrade to JDK 17 using G1 from JDK 8 using G1. The blue line here shows the percentage of wall clock time spent in GC. The gray area is the same metric from last week, so to make it easy to compare to last week. The brown line is the average pause time, and it's connected to this axis here. So as we can see, the switch happened somewhere during July 8th, and the pause time drops almost to half. So basically the same thing that we saw on our benchmarking, but it's extremely nice to see that that is also the case in a real-world application. Same thing for the time spent in GC, that is also almost down, or maybe even more down than to half. So pretty great improvements seen from just upgrading the JDK. Now in 2024, they are starting to look at upgrading to generational CGC or to JDK 21 to be able to use generational CGC. This is one of the main drivers behind them wanting to move. And by doing so, they have seen that they are able to reduce the number of errors in their systems. There's actually a really good blog post on this. I haven't included the link here, but search for Netflix and bending latencies and you'll find it. And they were able to cut down a lot of their problems by using generational CGC. And they actually decided to use generational CGC as their default collector for applications running on JDK 21. And this was somewhat a surprise to them. And I actually got a quote that I want to share, or I took this quote from their blog post, making sure that I could use it. Left unquestioned, assumption and expectations could have caused us to miss one of the most impactful changes we made to our operational defaults in a decade. We'd encourage you to try generational CGC for yourself. It might surprise you as much as it surprised us. And the surprise he's talking about here is that CGC worked well for all different kinds of heap sizes. They expected that since CGC doesn't support all the features that some of the other collectors supports, generational CGC would mostly be usable for really large heap, similar to what I said earlier. But it turns out in their workloads, it's good almost all the time. So instead, their application owners have to opt out of using generational CGC if they're using JDK 21. So from our point of view, this is really a success story. The next company I want to talk about is maybe not as well known, but Mercado Libre is a very large e-commerce, fintech, and logistic company in Latin America. It's present in 18 countries, more than 100 million active users, and they have more than 8,000 Java microservices. They are currently mostly on JDK 17, some on older releases as well. But they're looking to upgrade into JDK 21, and for them, the main drivers are Loom and generational CGC. I got a quote from them as well. This is a fairly long one, but bear with me. Mercado Libre is starting the journey of migrating over 8,000 microservices to Java 21. As an early step in this transformation, we migrated our streaming data service, which handles over 10 million incoming requests per minute and 40 million outgoing requests per minute, to Java 21, leveraging Loom and generational CGC. This migration resulted in significant performance improvements, including a 50% reduction in threads, a 25% reduction in CPU usage, a 20% reduction in memory usage, a 30% reduction in latency, and a 25% improvement in garbage collection indicators. These gains not only improved our response times, but also enabled us to handle the same traffic volume with fewer virtual instances, optimizing our infrastructure costs. This demonstrates the power of Java 21, Loom, and generational CGC in enabling high-performance, scalable data streaming applications. And yeah, this is a long quote, but I really think it shows the things you can get by upgrading and making use of the latest Java feature. They actually did some code changes to really leverage all the performance benefits from Loom. So this is not just a straight upgrade from 17 using G1 to 21 using generational CGC, but also some code changes. And sometimes that will be needed. But yeah, once again, a pretty amazing success story. The next one is an internal Oracle team, so the OCI object storage team. OCI is the Oracle Cloud Infrastructure, and there are a lot of applications in there are currently looking at upgrading to a more recent JDK just to gain all the performance benefits that you get by doing this. And the object storage team is no different. They are mainly a throughput-oriented workload, but they also care a lot about the time to first byte. So having a balance between latency and throughput, and then you might guess G1 provides this very good balance. So they are currently or have just upgraded from JDK 8 to JDK 17 and were able to share some results with us. And here we have a chart showing their put and get throughput from this service. And they did the upgrade late November 29. So here you can see the bump. We don't have any scale here, but this is something like a 20% improvement in both get and put performance for their service. So this is the throughput mean values that we're seeing over time. If we instead look at the time spent doing GC in their workload, we do see that this also improves quite significantly after the upgrade. So before the upgrade, we had something like 1 to 2% time spent doing GC, and after the upgrade, more like 0.5%. So pretty great. A short quote from those. We have strong data showing that the JDK 17 upgrade has improved our throughput with roughly 20% using G1. Also extremely nice to hear that a real-world application see the same thing that we do see in our internal benchmarking. The next slide is not from the outside, but it's using a real-world application, Cassandra. Many of you probably know about it. It's a distributed NoSQL database. It's widely used, and it's a proven technology. It's used by us in the GC team to have something that is more real-world-like than the usual benchmarks that we run. And we really think it's good because it highlights a lot of the different aspects that we care about. You can see both throughput, latency, and in some cases also throughput changes to the GC. And I want to show you 2 slides here as well. Now I'm not comparing against JDK 8, but instead showing the different GCs using JDK 21, or I'm actually focusing on CGC and G1, since those are the 2 that really provide some or really good latency results. What we're looking at here is Cassandra running with a 32 gigabyte heap, and we're looking at the average latency first. And the red line is CGC, single generational. The green line is generational CGC. Then we have 2 G1 lines. The lighter blue one is G1 with a pause time goal set to 50 milliseconds. And you might be surprised that you see G1 and being lower than generational CGC, and we still say latency, but that's because we're looking at the average latency. And on average, the GC pauses don't affect the transaction. So if you look at average latency, that's more of a throughput metric. So we can see that from a throughput point of view, G1 is doing slightly better than generational CGC, and yeah, significantly better compared to single generational CGC. And yeah, to be clear, what we're looking at here on the x-axis is I'm increasing the number of clients and looking at how that affects the latency. But the more interesting slide might be the next one. And here we're looking at the P99 latencies. And as you can see, single generational CGC, when we added more clients than 75, couldn't really handle this workload. So we started seeing what's called allocation stalls with CGC. And if you're running CGC and start seeing allocation stalls, you should really look at your configuration, either adding more heap or more concurrent GC threads to allow CGC to finish its collections in time. Because if you run into allocation stalls, the performance is no longer deterministic. With generational CGC, on the other hand, we don't experience those, and we're able to keep the worst case latencies extremely low. So this is 4 nines. Not entirely sure why I'm not looking at the max pause time here. But yeah, probably the benchmark does something strange, or the way we're running this Cassandra setup is doing something strange. But overall, the worst case latency is extremely good with generational CGC. Looking at G1, we can see that the default pause target it's keeping it, regardless of how many clients we have. Pushing the pause time goal down for G1 to 50 milliseconds, it's able to keep those at lower load. But as we increase the load, it's hard to keep this pause target. So this is something that we can improve on with G1. trying to keep it lower than what we have here and then, which is close to 100 milliseconds. Yeah, that was that for the performance numbers. And just a few words about the future before taking questions. So we of course want to keep improving. There's always things to improve when it comes to GC. We have a lot of more exciting feature for CGC, as I mentioned. We want to make the generational mode the default, but we have a lot of other interesting things that we want to try out. Having a fully concurrent collector allows you to experiment with things that you can't do with the Stop the World collector. So this is, yeah, expect more in the future to come here. When it comes to G1, something we talked about basically for the last 5 or 10 years is that we want to improve the throughput even more. And as you can see, we've improved the throughput for G1 already, but much of that comes from us improving the work inside the pause time. And having shorter pauses, of course, means that more time can be used by the application, increasing the throughput. But we're also wanting to improve the throughput while the application threads are running. So we want to improve what's called the write barrier of G1. And recently, we've done some really good work in this area, and hopefully going forward, we can see even better throughput with G1. And as I mentioned, continuing to work on footprint reductions is also something that we really want to improve, especially when it comes to parallel and CGC. There might be some more things that we can do for G1 as well, but as you see in the slides, G1 has improved quite a bit in this area already. So if you want to stay informed and know what's going on and what's happening in the Java realm and in the GC world, here are some links. We have the GC tuning guide. This is a live document that is updated for each release. And you can find some basic GC information in there and some tuning advice. You should also head over to the Java developer portal at dev.java. A lot of good tips and tricks there. If you want news and views from the likes of me, head on to inside.java, where we have blog posts and videos from the Java team. If you're interested to contribute to Java itself, you can join the mailing lists and be part of the discussions. So find that out on openjdk.org. And if you're interested in the JDK code, that's available on GitHub. Head over to github.com/openjdk. And of course, Java and OpenJDK are available on Twitter and other social networks as well. So with that said, only one last slide. So the key takeaways from this presentation. Well, there have been massive improvements since JDK 8. So if you have the possibility, you should really look into upgrading to a more recent release of Java, because the performance benefits are enormous. And of course, you need to choose your GC wisely. Depending on your use case, which GC you're using is really important. Do you care about latency or do you care about throughput? Which GC should you use? This is questions that you should ask yourself. And lastly, you should keep upgrading. So once you've moved past JDK 8, moving to newer releases is not that hard, and you get performance benefits for free, and you get to use the latest and coolest Java features. So keep upgrading. And yeah, that's it from me. Any questions, I'm willing to answer them now, or if you come down to the Oracle booth later on, I will be hanging out there. Not sure if I see any questions, so yeah, one here. Blinded.
So that Java 22 has a new GSR related with G1. I don't know if comments related with GNI, concurrent work or something like that.
Oh, is that the region pinning? Yes. Yeah, so that did go in JDK 22. So that's a different way of handling JNI. So if you have objects that are used by the native interfaces, we have a new way of pinning heap regions so that they are not used. They can't be collected because objects in those regions are used by the native code. So that's a different way of handling that prior to what we had before. It shouldn't affect the performance a lot, so it's not something that really shows up in those benchmark results, but it's a way to better handle the native interface integrations. Any other questions? Yeah. Sort of. I have a blog post about. I'm not entirely sure that I posted one for JDK 21, like with those latest results. I have a similar one showing the ones that we had for between JDK 8, 11, and 17, but I mean those are outdated now. But yeah, I'm not completely sure if I updated that one to include 21. Hopefully I did, but if I did, you find it on inside.java and search for my name, Stefan Johansson. Otherwise, I should probably look into creating a blog post with those results. Any more questions? Yeah, I'm so blinded. Sorry. Yeah, you.
The biggest issue all Java developers have is interpreting GC logs.
Yeah.
You need to be GC engineer to able to understand everything.
Yeah.
Any improvements to make them user friendly. I'm not mentioning JMC.
Yeah.
But robots you can get from production and like understand what you do next.
Yeah. So I should probably repeat the questions, and this question is regarding GC logs and if we have any plans to improve them so they are easier to interpret by Java developers. And currently we do not have any such plans. I think logs are logs, and it's good that we have tools that from the outside can help out inspecting those. And it's extremely hard. We try our best to make the logs like on a high level that they should be easy to understand, like how long is the pause time and things like that. But when you start really investigating what problems you have, it's gonna be hard, and you're gonna have to dig down into that. So currently, no plans on improving that. Sorry.
But maybe so this high level information summary that there are problems.
Okay.
Yeah, because what we get from our developers when they come to JDK team,
Yeah.
they simply there is no issues at all. So they just alert about high usage of Java hip up to DC, or they don't know the target latency. So if there is no issues, then it looks like something. So say that no issues.
Yeah, and of course that is really hard, because to know if there is a real issue, you also need to know kind of what the requirements that certain Java application has on, like when are we having high load. So in many cases, if I understand you correctly, it's hard just from the GC's point of view to really do anything about that. So usually you have to have an outside system knowing both about what your requirements are and trying to work that together with the GC information. And apart from the GC log, you also have JFR. You mentioned JMC, but you have JFR, which might be a better source for this information if you want to do programmatically things to try to understand why am I seeing higher latencies at a certain point, because it's easier to program against JFR events.
Every Java developer does not possess the skills to go to the level of JFR.
No, that might be true, and if you have ideas on how to improve this, I would be really happy to hear about those. So please come and speak to us, and if you have any ideas on how we could improve on this.
Internal heuristics, for example, the one that you mentioned as a target latency.
Yep.
As soon as we above this target latency, looks like the system in a critical condition.
Yeah.
Somehow we can say this.
Yeah.
Currently, I need to go through a lot of lines and blocks in order to understand my purpose.
Yeah. Thanks.
Requirements are not met.
Yeah. I understand that, and that's that's something that we could probably improve. There are some logs when you go over the pause time goal, for example, but maybe that should be configurable to be an even harder log to really show that you have a problem here. Yeah, I see the time is up, and feel free to leave if any of you have more questions. I'm super happy to talk about GC, so feel free to approach me at any time.